climate change cannot be addressed without changing American agriculture in some radical ways. Next to energy production and petroleum in particular, industrial agriculture is the single biggest contributor to global warming. This presentation first offers some context about agriculture in Iowa and the wicked problem it presents to water quality in particular when exacerbated by climate change, which current practices are contributing to. And I'm going to describe an MLA design studio structured to try to address the problem using geodesign and a parametric modeling approach, an integrated approach, with an example and discussion at the end. The studio is an MLA capstone studio that ran in parallel to the IGC project headed by our wonderful students in Alenka Poplin, but did not comply with IGC, so can only be considered loosely allied with it. So agriculture in Iowa has changed radically in one generation. One can see how diverse the farms are and frankly more sustainable and less wasteful they were even just a generation ago, and how they've converted to monoculture. So this idea that a family farm is feeding the world is a myth. And 92% of Iowa's land is devoted to agriculture, which is the highest in the nation. And yet most of this looks like this, where soy and corn are rotated every year or not rotated at all. And this is contributing to soil deterioration, erosion, runoff, and pollution to the Gulf of Mexico, not to mention our capital city, Des Moines, Iowa, which I'll get to. So let's see. So we're contributing through two watersheds, the upper Mississippi and the Missouri. Iowa is right here, so these two watersheds are contributing to the Gulf of Mexico in a hypoxic zone, which has really worsened dramatically since this data was collected. And it's also, these nutrient pollutants are contributing to poor water quality in Des Moines, Iowa, because it sits at the bottom of the watershed, and therefore there was this famous suit, which you may have heard of, this lawsuit, which sued 3 counties in northwest Iowa to try to force them to comply with the Clean Water Act, which so that they wouldn't dump excess nutrients from runoff, erosion, and into the Des Moines River, the Raccoon River, and so. The case was dismissed, as you may have heard, and so any compliance with climate change improvement has been left to be voluntary for farmers, and farmers are not adopting best management practices. So I saw in that an opportunity for landscape architecture to generate not only ways for them to adopt best management practices by showing them in 3D what these might look like on their farms, but also quantifying their impacts on reducing the climate change contributing factors that were coming from their farms, resulting from their practices. And therefore, so the studio was born, and we've run it sort of twice now, and so I'm going to show you, first tell you what the goals are. So we wanted to parameterize best management practices, which meant model them in 3D such that their dimensions and their performance could be quantified and visualized, and to do this for specific farms. So this was a farm scale undertaking, several farms, where we took 6 farms from different landform regions from Iowa and applied these methods with groups of students. And then we looked at how these best management practices would impact the erosion, nitrate concentration, and runoff, and in some cases some other variables for these 2 time horizons. And the goal was to incentivize farmers to implement them because they are reluctant to do so because they don't know what these best management practices look like and what benefit they'll get from them. So the BMPs that we focused on were saturated buffers, wetlands, cover crops, and bioreactors, which is a subset of a much longer list, which we felt these 4 were the most relevant to specific farms. So here are some examples of how we parameterize these. So we wanted, so this is a parameterized buffer strip where the dimensions of them and the visualization of them were quantified and put and expressed to scale, and these would be entered into a kind of library of primitives for designers to plug and play with for specific farms, so sort of generalizing their geometry so that they could be built. And so wetlands, the same thing. So what are the key dimensions, inputs for a wetland model, and how could these be adjusted for different site circumstances? And then bioreactors, what's a bioreactor, and how would it look and feel on a particular farm? And cover crops, when to plant them, what should be planted, sources of seed, and so on. And so here's an example. It's really a collage of different projects where we took a typical or a common soy, corn, binary rotation farm and modeled the existing conditions of it. And then in Rhino and in Grasshopper, we used Grasshopper as a kind of linked calculator for quantifying the dimensions of these BMPs interactively so that the farmer could try out various scenarios and various sightings of the BMP on a specific farm, and also could get some real quantified understanding of what the benefit would be. And so this project was divided into 3 sub-watersheds on the farm, and each one received, each sub-watershed received attention for different options and what the consequences would be for the different time horizons and for the different BMPs. And so I'm going to kind of go through these quickly because I don't have a lot of time. And show you a summary slide, which is what we would often present to the farmers at our interim and final reviews for reaction and feedback. And the feedback, anecdotally, has been very favorable, and that they would really like to have services like this provided so that they can comply in more they would be more willing to adopt some of these BMPs in the future. That's what I prepared to share with you today. Thank you.